Okay, hearing no questions now, but giving you guys the right to change your mind at any moment. I'd like to keep talking a little bit about minimum spanning trees before I do the problem of the day today, just because it'll give us a little bit more of an angle to talk about minimum spanning trees. But as we talked about before, minimum spanning trees are the lightest weight in terms of total edge weight of any tree that connects all the vertices in a graph. Um, and we show how to do it with Prim's algorithm to find the optimum by starting on one vertex and kind of growing a tree out by always taking the cheapest edge that would expand it. And the amazing thing was that that it was you know what you call it. It would give the correct algorithm answer whenever the you know, for any graph, even though it was making a local decision, a greedy choice. Um, and we saw that it was an n squared algorithm if we implemented it right. Any questions about Prim's algorithm? And you're going to see Prim's algorithm again today, whether you like it or not, in a different guise. So if you have questions, I'm happy to hear it. Now, Prim's algorithm was n squared. The maximum number of edges in a graph would be any graph would be n squared. Okay. Clearly, any algorithm to find the minimum spanning tree that any algorithm would find the minimum spanning tree in a graph in a dense graph is going to have to take at least n squared time. So Prim's algorithm is the best you can hope for when the graph is dense. But when you're sparse, okay, what you call it? When the graph has relatively few edges, when m is little o of n squared, the algorithm I'll talk about today, Kruskal's, can be fastest. And it's a different greedy idea on how you find a minimum spanning tree. Basically, it's going to start by repeatedly adding the cheapest edge that does not create a cycle. So I walked through this last time, but Prim's was started at one vertex and added the edges in a order like this, okay, radiating out from the tree. Prim's always took the cheapest edge that would not create a cycle, and it might create independent components, like here at this point in the algorithm. We would have two independent components in the graph. That doesn't bother Prim's algorithm one bit, Kruskal's algorithm one bit. Okay? Any questions? So what was Kruskal's algorithm? We were basically going to sort the vertices, sort the edges, excuse me, based from cheapest to most expensive, and then keep adding the edges in the order until they create a cycle. Any questions? Does anybody want me to go through Kruskal's algorithm again on this graph? I did it at the end of last class. Anybody want to see that? Not seeing it. Okay. So I think the mechanics of Kruskal's algorithm should be fairly simple. Okay, if you understood it. In fact, let me just see if I write it down just to make sure people see it. What is Kruskal's algorithm? Basically, we're going to sort the edges from cheapest to most expensive. Then for each edge we insert, we're going to go from cheapest to most expensive. See whether it creates a cycle with the edges we have already added, okay? If it does create a cycle, we're going to throw this edge out. If it doesn't create a cycle, it can still be a member of our minimum spanning tree. And so we're going to keep doing this. And so it should be clear that the algorithm is going to be something like m log m to sort the edges, okay? And then something like m times the time it takes to tell whether inserting this edge will cause a cycle. We know of a way to do that with depth first and breadth first search in order n time. So this will give us an order, as we look at it, m plus log n plus mn, meaning an mn algorithm. But in fact, there's actually going to be a faster way to do it, and that I hope to get to a little bit later. Any questions about what the basic mechanics of Kruskal's algorithm are? How we test for the cycles quickly is going to be slick, but the basic mechanics you should see. The real question is, why is Kruskal's algorithm correct? Why, if we keep taking the edges from cheapest to more expensive and add them if they don't cause a problem, is that going to yield the correct answer? Okay. We're going to give a proof by contradiction in many ways similar to the proof of contradiction that we had for Prim's algorithm. If Prim's algorithm is not correct, what do we know? There's got to be a graph where it gives the wrong thing. If there is a graph where it does the wrong thing, then there's got to be a place where Kruskal is adding an edge, and suddenly that breaks the possibility of any minimum spanning tree with what we've added so far. You know, even on the graph where Kruskal's are supposed to get it wrong, the first couple of edges might be right. Where did it go bad? Okay. Well, now what we've got to argue is that when we add a, this new edge that's impossible, okay, what are we going to do? Suppose, let's think back to what we had before. Suppose I am trying to run Kruskal's algorithm, and I try to add an edge, and you tell me, on this graph, before you added the edge, all the black edges were okay. But now when you add this edge, okay, you can't have a minimum spanning tree anymore. I'll say, oh, show me your minimum spanning tree. And the guy says, well, I will continue this to a minimum spanning tree. And what we know is that when you do this, adding this edge that I wanted that you didn't want will create a cycle. Okay? Now, is there an argument that if it creates a cycle, I couldn't have gone wrong with that edge? Why, if I take this cycle, okay, how can I argue that if this is the tree you get that did not include this edge, okay, that in fact you can't have a minimum spanning tree, or you can't stop me from having a minimum spanning tree? Why? Adding any edge to a spanning tree is going to create a cycle. What do I know is the heaviest edge on this cycle? Okay, let's think about it. Could this be the heaviest edge on the cycle? Could that be the heaviest edge on a cycle? This one that was already in the minimum spanning tree, but that Kruskal's algorithm picked first? No, why not? Why not? The reason is because we picked these edges, we sorted these edges from cheapest to largest, right? We inserted them from cheapest to largest. What do I know about this edge? This black edge was inserted before the red edges. Well, darn right, that edge is going to have to be cheaper, or at least no more expensive than the red edge. But more to the point, if Kruskal's wanted to add this edge, what do we know if Kruskal wanted to add this edge? It knows we didn't have a cycle so far. Is that right? If these edges in the graph, if these edges in the, let's try it like that. If these edges had already been picked, okay, we would have had a cycle, and we would not have picked the this red edge for Kruskal's algorithm. The fact that we picked it meant that based on the edges so far, this edge did not, this edge did not create a cycle. So what do we know about at least one of the other edges on the minimum spanning tree, on the tree that your algorithm picked? Okay, what do we know about at least one of these other edges, these green edges? Okay, what do we know? Because when we picked this edge for Kruskal, it didn't have a creative cycle. At least one of these edges had to be picked later than this edge. What does it mean if those edges were picked later? Somebody, show me you're paying attention. What is it?
They're heavier.
They had to be heavier. And what's the problem if one of these edges is heavier? Well, what if I add the edge I want and get rid of it, the edge that you had? Let me go back here. If I took that one of those heavier edges from the cycle and delete it, replacing it with the one that I wanted, the net cost of the tree is going to go down, isn't it? So how did you have the minimum spanning tree? When how can you say I went wrong? You could not have produced a lower cost spanning tree than I would. Because I can take your spanning tree, add the edge you rejected, remove, there's one of the edges on that cycle has to be heavier than me. Because if not, I would never have picked myself in Kruskal's algorithm. And therefore, deleting it, the heavy edge, and replacing it with me leaves a spanning tree that is certainly no more expensive, okay, and was what I would have produced by Kruskal's algorithm. How many people sort of get that idea? The reasoning again, okay? When we added this edge, there was no path between X and Y, or else it would have created a cycle. If it did, I wouldn't have picking it. So when I add this to the optimal tree, it will create a cycle, because adding any edge to a tree will create a cycle. But at least one edge on this cycle is going to be added after me, so it must be heavier. Doing this swap will certainly not increase the weight of the tree, and so you couldn't have gone wrong making that pick. Any question? Any questions at all about the reasoning why Kruskal's algorithm is correct? Okay, can you repeat what I said about a cycle being created if I add it? Again, what's happening here? I have got a world, sorry, let me clear it out one more time. I have got a world where I'm trying to run Kruskal's algorithm. You're telling me that if Kruskal's algorithm was wrong, there was a point where I made a mistake, and you're showing me this as being the example that I'm bad. I'm going to say, oh yeah? I'm going to take that edge, set it aside, and then ask you to show me a better spanning tree. Okay? And you're going to say, yes, this was the minimum spanning tree. Or something like that. And what do I know? If I now add back the edge you rejected, it will create a cycle. And on that cycle, there must be at least one edge heavier than me, or at least no lighter than me. Because if not, I would have picked it first. Okay? And it would have had, if the cycle was there when I picked X, Y according to Kruskal's algorithm, I would never have selected it according to X, Y. So therefore, at least one of these edges was later, was heavier, and that's the problem. Any questions with the basic idea? Okay, so the amazing thing is that Kruskal's algorithm is correct. Any questions about Kruskal's algorithm? What I'd like to do is to show you, take a little time and show you why it's kind of how you can in fact make Kruskal's algorithm run faster than m times n. If we look at the algorithm, again, we will start by sorting the m edges. That's going to be m log m. Then we're going to go around m times and have to test whether or not adding an edge to a cycle, okay, edge is going to create, adding the next edge will create a cycle. If it would create a cycle, we discard it. If not, I'm going to add it. For me to make this algorithm run in something like m log m time, I need to be able to do this test. Can adding a cycle, adding a new edge, create a cycle? I've got to be able to do that in something like log n time, okay, in order to realize my bound of something like m log m n. Any questions? Actually, here's a question. If I have something running in m log m, where m is the number of edges, why do I say that this is the same thing as m log n? Let's start with this for a second. You may think I'm being slippery. Sorting takes m log m time, we think, because we've got m edges, right? But what do we know about m? How does m and n relate to each other? Is there any relationship between the number of, big O-like relationship between m and n? I'm seeing that the number of edges m is big O of n squared. Does everybody agree that's the densest possible thing? What is the log of n squared?
2 log n.
2 log n. Does everybody see that since the number of edges is polynomial bounded by n, okay, in fact, it's perfectly fair for me to say that something that is m log m is really m log n. This sounds a little bit better, so that's why I'm going to be saying it that way. Any questions? Okay, in order to do this, though, I've got to test for cycles quickly. Let me show you a fast way to test for whether or not this has a we can create a cycle, and we're going to do it by having a data structure to enable us that will enable us to do two things. Our data structures are defined by the operations they do. A same component test is going to ask myself, is vertex 1 and vertex 2 in the same connected component? Certainly, the only way adding an edge is going to create a cycle is if the two vertices are in the same component. When they're in different components, they don't create a cycle. Okay, so this is really the heart of what I need to answer. But I have to also update, because when I add an edge, suddenly those two components became one. And so it's going to change, how hard it is to, change the answers of what same component is. So this is like querying my data structure, and this is updating my data structure. Okay? Any questions? Do we agree that if I could have an algorithm that could test whether they were in the same component in log n time and merge two components in log n time, okay, that would be a very good, that would enable me to do this whole thing in m log n. Okay, do people agree that if I could do this, this would solve my problem? Yes. Okay. Now, how would you build a data structure? Just to think about it for a little bit, so you're impressed by this a little bit. What is the right way? What would you think of maintaining what the components each vertex is in? Can anybody think of a data structure that would let me to do that?
Wait, I have an idea. What if you had like a list and you had like the parent sort of node for each vertex, like the predecessor node? So, and then if you have a vertex and you have like a predecessor node, then you know that they have to be part of the same component.
Okay, that's a better idea than I was looking for. Okay, and we'll talk about that because that's actually basically what we're going to do. Just so you get a better idea, what I thought you were going to say. What if I kept an array from 1 to n, and it told me what the component number each vertex was in, right? If I had an array which told me the number of the component each vertex was in, if I wanted to know whether 1 and 4 were in the same component, I could simply test this, right? With this kind of a data structure, I could do my same component test in constant time, right? Is 1 and 2 in the same thing? The trouble is, once I add them, I've got to change all the members of, let's say, component 4 to component 2. And this looks like it would be order n. Okay, so just doing the naive way of representing this looks like it won't work, right? Any questions? But the idea here is, again, this is basically just what anyway, this is basically just what I said Kruskal's algorithm was. Okay, what is the data structure that I want to do? I want to have a data structure that is based on maintaining sets that is going to, I'm in trouble now. Hold on a second. Wait a second. Okay, something happened here, sorry. I think I'm still up. Am I up? Hold on. Wait a second. Okay, something may have happened. Let's just keep trying here. Let me try one more time. Every once in a while, this thing breaks, and let me try again. Okay, so what is the idea behind the union find data structure? We're going to represent, as was sort of hinted at by the students' idea, we're going to represent each set by a, by a tree, okay? And what we're going to do is find is going to tell me the root of a tree, and union is going to merge two trees together, okay? And the idea here is we're going to maintain every subset of vertices by a rooted tree where things point up to the root. And we will then walk up the tree to find the root. That's kind of like finding the parent, as he was saying. And if we have a tree where, let's say this is 3, 5, 7, let's say these are the vertices in component, in a particular connected component. The root ultimately of 4 would be bunk, 3. The root of 1 is going to be 3, okay? If we have a tree, all the vertices in a component, such that we can walk up the tree, okay? The root gives us a unique identifier of it, okay? So to tell whether two vertices are in the same component, okay, all we have to do is to find what is the root associated with the two vertices. If the root's the same, they're in the same component, otherwise they are different. Union is going to be the idea to merge two of these trees together. How can we merge them together? Well, what if I set the root of this one to point to the root of that one? Does everybody see now when you do a find on vertex 8, it's going to bop up to 3 being the ultimate root, right? Does everybody kind of get that idea? So if we represent these trees as a, as trees point with roots, edges pointing upward, okay, we can climb the tree, okay, and do a find in time proportional to the height of a tree, and a union, okay, in time proportional to the height of the tree, okay? What is the height of the tree going to be? Well, I see a lot of people saying log n. They're saying that aspirationally. We want it to be log n. But that depends upon what happens when you do the unions. Isn't that quite right? Which tree do you want to merge to? So here I merged this tree, the head of this tree, to the head of that tree. I could have also taken 3 and pointed to 9. Which would be better? For me to merge, take the union of 3 and 9. Should I have had 9 point to 3 or 3 point to 9?
I think 9 point to 3 because
Why do you want 9 to point to 3?
the height is smaller.
Did everybody see that if I take the shorter tree, okay, and point it to the taller tree, I'm not increasing the height at all, right? The only time I will increase the height is if they are 2 trees of the same height. Or I have the taller tree pointing to the right, to the shorter tree. Okay? So if I could maintain which tree, if I knew the height of each tree, that would be enough to let me make my wise decision of what to move. Okay, merge. Okay, so what is a union find data structure? This is actually a very clever little data structure. I'm going to maintain for every node, what is its parent? For the root itself, or a singleton element, it's going to be its own parent, okay? And now walking up the tree is simply going to be, following up the pointers. So 7, the parent of 7 is 2, the parent of 2 is 4, the parent of 4 is 4. Bingo, the answer is 4. Okay? And to merge these two, if I wanted to merge these 2 trees together, all I would need to do is to set the parent of 3 to be 4. Okay? And I would like to do it in a way that shorter trees get that tall trees point to short trees. Take it back. That I have it. The short tree points to a tall tree. Any questions? So if you look at the code, it's actually quite simple to do this. Okay. Now the key is, again, if I'm not careful about what I make the root, very bad things can happen. If I just merge it arbitrarily, I could get a tree that's going to have a height of n. Okay. I would like to make it so that, I limit the height. It turns out it's hard to keep track of the height of a tree after you merge something. But it's easy to keep track of the number of nodes. And what if I always say I'm going to have the tree with the fewer number of nodes going to point, with the fewer number of nodes be the child? Okay? If for every node, every node, I know the height of it, the number of nodes in its subtree, okay? To figure out which one is bigger or not is just comparing a number. To merge, what is it, the number of nodes in the merge tree, it's just adding them up. So it's relatively easily to do. what is the number of times I can double the height, the number of nodes in a tree? Let's think about it. Let's think what the height is. If I have a tree of height n, what is the shortest number? Let's say I have a tree of height h. What is the minimum number of nodes I can have in a tree of height h? Does everybody see that if I have a tree, with more nodes, let's say that I have a tree here with n1 nodes and a tree with n2 nodes, where n1 is greater than n2, what am I going to do? I'm going to link this to this. Is that going to increase the height of this if this was the taller tree? Under what condition will I increase the height of the tree? What if they both had the same number of nodes? Does everybody kind of see that? Then I'm going to, in some sense, double the number of nodes and yet make one taller. Okay? Does everybody kind of see that when I'm merging equal weight trees, I am doubling the weight? The number of doublings I can do is at most what?
Log n.
Log n, right? And it should be clear, maybe it's not 100% clear, but it should be clear the maximum number of doublings I can do is log n. The weight of the heaviest tree after this is going to be at most log n. It's going to have been through at most log n doublings. And it's only on a doubling that the height is going to increase. So this is basically an argument that if you merge it so the light tree becomes a daughter of the heavy tree, it's going to be log n. Any questions about that? I have a fancier proof here, a more precise proof you can look at. But does everybody get the basic idea? So union find lets me do this in log n time per operation. And it's a useful thing to know. And even better things happen. There's actually even faster ways to do this merging. So the tree gets even shorter than log n, but that I don't really want to go through. Any questions? If you understood everything I said, you should be able to now believe that Kruskal's algorithm can run in m log n time. So for a sparse graph, this is a lot better than n squared. Any questions about that? Any better about Kruskal's algorithm? Okay. Any questions? Okay. And again, this is the code, but I don't think I really even want to go through it. It's pretty simple. To tell if they're in the same component, maybe I'll do it just because I'm here. Same component, find the root of one vertex, find the root of the other vertex. If they're the same, they're in the same component. Okay. And to find it, what am I going to do? I'm going to start from a vertex. If my parent is me, I'm the root. Otherwise, find the root of my parent. Okay, and this is a recursive thing that will take time proportional to the height of the tree. Any questions?
I have a quick question. So when would it be better to use prims over Kruskals?
When would it be better to use prims over Kruskals? So one is m log n, and one is n squared. So you tell me.
I would think it would never be better. Hold on. Wait. Never mind.
No, it's a good thing to work out, right? When when the graph is dense, this is n squared and this is n squared log n. So for dense graphs, prim is king. For sparse graphs, if it was at a linear number of edges, it would be n log n. And the Kruskal thing would be to use Kruskal.
I see, because m in dense graphs is n squared.
Yeah. Right. Any questions? Okay, any other questions about minimum spanning tree algorithms? Okay. Okay. If not, I'd like to now get to the daily problem because I think we get a couple of other ways of thinking about it. What is the daily problem today? The problem of the day said we are given a minimum spanning tree, okay, of a graph. And we're given a new edge that's going to get added to the spanning tree. Added to the graph, excuse me, not the spanning tree, to the graph. Okay? Given efficient algorithm to update the minimum spanning tree, okay, with the new edge. Okay? So you're given a graph, you're given there's a graph G, which is big and dense and complicated. There is they're giving you the minimum spanning tree of this graph. And they are giving you a new edge. Sorry, hold on. And they're giving you a new edge. Did this new edge increase or does this new edge now find the new minimum spanning tree of the graph? Any ideas how to do it?
The way that I sort of started to do it was that you could sort of, like you do in Kruskal, you can sort of find all the weights of all of the edges, and you know that all of the edges that have a lower weight than this edge that you just added would sort of have to be part of the MST.
Yeah.
And then at this point now, you can basically add this edge into the graph, and then all of the edges, out of all of the edges that have a weight greater than this edge, some of them are now not going to be part of the MST anymore, or because you added this.
I'm going to stop you right now because you're wanting to go back to this big graph here. And you're trying to say, let's add this edge to the graph, and then maybe I don't have to look at the whole graph. You may have to look at a large fraction of the graph by what you're telling me. So I'm not understanding that. The question: are U and V already in the tree? Well, by definition, yes. The vertices are all in the tree. In any minimum spanning tree, it's got to cover all the vertices. Now I'm adding a new edge. Okay, can we update the minimum spanning tree? Okay. Any questions? Any ideas how to do it?
So my idea is to run through all the edges in the tree because we know that there's going to be at most n-1 edges. And then if we remove that edge or a particular edge, we can see if the edge E is heavier than it. If it is, then we know that E can't be in the MST. If E is lighter than the edge.
Well, what you said, and I'm going to try to hold you to it for now. You're saying that you go through all the edges in your tree and see if you get one that's heavier than edge UV. That's not going to do it. What happens if this edge was of weight 5 and this edge was of weight 100? Here we have an edge that is lighter than than an edge in the spanning tree. Does that change the minimum spanning tree?
No, because we will have a cycle.
So any edge that is outside the cycle is not going to be helped by this, right? Does everybody see that? So what do we need to do? Okay. I think, tell me.
Okay, maybe we could like traverse through the spanning tree T, starting from the vertex U, because we're adding an edge UV, right? And then we go through it until we reach V. So when we reach V, we start to go back and look for the maximum weight H along the path.
That sounds very good to me. So she's saying start a DFS or a BFS, whichever letter of the alphabet you like better, and build a tree of discovery. Of course, since all the edges are a tree in this case, there's not going to be, the trees are going to look the same essentially once you start from one place. Now, if you start from U, you're eventually going to find T, V. And the real question of whether or not there is an edge, you are going to lower the minimum spanning tree if and only if there is one vertex on the cycle whose weight is 6 or greater than 5. Does everybody agree? If I can find one edge there on the cycle that's greater than 5, then I am better off eliminating that edge and adding this one, and I will have a cheaper spanning tree. So what is she saying? Start from that vertex, do a traversal. When you discover the vertex V, bop up the parents and ask yourself, for every one of these edges, are you heavier than V? Okay? Once you find the heaviest one of these, okay, you will replace the heaviest one of these on this path with that vertex, that edge, and you will have the new minimum spanning tree. Any questions?
So just to be clear, we're doing this traversal on the MSC without UV?
Right, so there are a couple different ways you could do it. One way is you do the traversal on the minimum spanning tree without the new edge. Then once you have discovered this, you know that path up the tree is going to be the edges. That would be the rest of the cycle. You walk up here and you find the biggest edge you encounter. That is the one that you would want to swap out for your new edge if it is, in fact, heavier than the new edge. Okay? Any questions?
Yeah, that makes sense, but like, can you go over again how you know that inserting an edge connecting U to V is gonna create a cycle?
How do I know? I know because in any tree, a tree is by definition the minimum connected graph. Right? Isn't that what a tree is? A tree is a graph that is connected that has no cycles. It has exactly n minus 1 edges in a tree on n vertices. Right? Adding any edge to any tree is going to create a cycle.
Got it. Thank you.
Okay? And now the question is, the only way that I can improve my spanning tree is with this new edge. Is this new edge going to let me do something I couldn't do? And that's going to be true if and only if I break the cycle. Okay? Any questions about that? Okay, do people kind of get that? Another way to have done the same thing, by the way, would have been to add the edge to the graph, the tree, and then do a depth first search. Then the first back edge I have is going to be that cycle. And then I know where to walk up and down. But I kind of like the way that she did it. That seems maybe even a little more elegant. Any questions about this? How we found the minimum spanning tree? Okay. Okay, that's the problem of the day. Any other questions about minimum spanning trees before I move on? Okay. Okay, so let's now talk about finding shortest paths in graphs. And shortest paths in graphs is finding the shortest path in a graph, okay, is, a classic problem that you knew was important, okay, before you came in here. All of you had, well, in my era, you had GPS. In my era, you had maps. Then you had GPSs. And now you've got cell phones running Google Maps, right? You know that when you're driving, you want it to tell you the shortest path from here to someplace else. Kind of one of the most amazing things is Google has such a fast algorithm to find the shortest path between any two places in the country that they won't even charge you for it if you stop and think about it, right? It's such a fast computation. If you want to find the fastest way to drive from here to a particular bodega in Bolivia, okay, you can go into Google if you have the address of this that you want in Bolivia, okay? It will find you that shortest path amazingly quickly, okay? It's clear for transportation problems, you always want to find the shortest path. But there's a lot of other problems where finding the shortest path between two nodes in a graph, okay, are, are kind of important. When you have an internet routing thing, let's say you have a communications network. Ideally, you'd like to send it, data from one node to another node in the network. What would be the best way to route it if you had a global control of this network? It would be basically the shortest path. When you want to figure out an upper bound on how long it will take for a message to get across, you're kind of interested in, like, what's the longest possible shortest path? What's the two nodes that are furthest apart from each other? Okay? There are a lot of problems that I want to claim reduce to finding shortest paths on graphs. And so if you come out of this class recognizing that, yes, there are fast ways to find shortest paths, and yes, if I could turn my problem into a shortest path problem, I can solve it by looking up Dijkstra's algorithm in the book, okay? That gives you a great deal of power in life. One example of how powerful finding shortest paths is was a problem that we worked on once to try to reconstruct text typed on a telephone keypad. If you guys have ever looked at a real telephone, you'll know that there's 3 letters on each key of a telephone. And if you wanted to type a message using those letters, somehow you're going to have to disambiguate which of the 3 letters you meant to type, okay? Unless you could try to guess based on, what you know about English words and English grammar and things like this. So we tried to build a system that would try to reconstruct text typed on a telephone, without having to specify which of the 3 characters at each position you meant. How did we do it? Well, we thought of this as a graph problem where the vertices were words and there was an edge between neighboring words. What do I mean by that? Here's a picture of what we were doing. Let's say you typed in this phone message, okay? There were, sequences of tokens that corresponded to words, okay? The convention we said was that you hit a star whenever you were finished with a word. Type word, star. Type word, star. Okay? And notice that when you type something on a telephone keypad where, you're specifying only 1 out of 3 letters, the code you get back for each word is kind of like a hash code, right? You can think of any word as reduced to a string of digits. And the problem is that many strings of digits can map to the same word, can map to multiple words, right? If you go on your phone, the same thing that you try to type cow, that's the same thing as boy. That's the same thing as any. That's the same thing as box, okay? How do we figure out which word you meant to type? Well, we're going to build a graph where there is a vertex for every word consistent with the sequence of tokens. We're going to add an edge between every word in one position and every word in the other position. See how this is kind of like a complete directed graph over here? Any one of the interpretations in position I maps to any one, points to any interpretation in I-1. and I plus 1. But what are we going to do? We're going to set weights on these edges. Suppose we have a weight between any two words about how much they like to be next to each other. Okay? How might we know that give me is a more popular pair of words than hive me? Can anybody, how might we figure that out?
I mean, I'm thinking like if you have like a word that you're currently at, like let's say you start with the word give, and then you would have words like me, which would have a lower edge weight than you or him or something like that. And so the lowest edge weight would be the edge that you would traverse and go to
Okay,
me.
so you want me to traverse the lowest edge weight. But what if I have a word like, let's say, you know, I'm now going to make this up. What? Okay, first of all, I was interested in how do you get those edge weights, and I'm going to say I'm going to tell you, well, way you might get that is by looking at a lot of text and counting up how many times does give me occur compared to of me, hive me, right? Okay, so I claim you can estimate these weights by looking at a text corpora. Okay, and figure out how much words like to be next to each other. Okay, now what he's trying to say is he's saying that if we do this, what is the best interpretation of a sentence? I'm going to claim it is the shortest path to get from here to here. Does everybody kind of believe that? If a lower weight meant more likely to be on this, to be what we would do, the right path would be give me a ring. Okay? Any questions about that? Now, one thing I would like to say, though, is I want to find the globally best path from here to here. The student said, oh, I know how you're going to find that. Okay, I'm just going to start from the first place and find what is the cheapest edge. He's going to say, okay, start from the first position. Find the cheapest edge. That'll get me to me. Find the cheapest edge outside of me. Find the cheapest edge outside of that. Can we find the shortest path from the beginning to the end by just greedily following the cheapest edge? Seeing someone shaking, now he's shaking no. Why is he shaking no? Well, he's hearing my voice. He knows he's got in trouble, right? Why is he in trouble? Okay. I'll claim that suppose we had a situation, like let's just say it was, you know, give, okay, sorry, let's say the possibilities here, trouble, or give, you know, let's say it was me, Skina, let's say this was another alternative, and let's say of. First of all, there's no law that, in fact, if you want to know, it could be that give Skina might be the cheapest wage. Okay, let's say that the corpus we analyzed was my textbook. You could imagine where this might be a cheap word, but maybe there was never a phrase, Skina a. Does everybody see that if you went through this in a greedy way, it is possible that this would be a very cheap edge? But this would be a very, very expensive edge, right? And if you wanted to find the shortest way from give to if you went down this first edge, you would be making a mistake. Does everybody do you kind of see what the point is? This is actually an important point. You might find the cheapest way, it might be cheaper to get from give to Skina than from give to me, but the total cost to get from give to A might be cheaper because the cost of getting from give to A would be give me plus me A. If give Skeena was very cheap, but Skeena A, again, it's very hard to get an A with Skeena. You guys should know that, right? This could have been very, very expensive, okay? So taking the greedy algorithm of always taking shortest edge, shortest edge, shortest edge, wouldn't give you the shortest path. That's why we need a special algorithm for it. Any questions about that? Do people see that? That's an important point. But if you know that there is, in fact, a fastest algorithm for finding the shortest path, now I've reduced my problem to finding the shortest path in a network. And I looked this up in Skeena's book. They tells you about Dijkstra's algorithm. Now their problem is solved. Any questions about that? Any questions about the application or why finding the shortest path is not just taking the cheapest edge possible all the time? Any question? Okay, that's good. If so, that's a good introduction. Again, like I said, I weighted the graph according to the probability that these two words would like to be next to each other. Hive me is rare, give me is common. I'm going to give me a better weight than hive me. Okay? Any questions? Okay, so let's now look. Does everybody see that finding shortest paths is a useful thing to be able to do? Okay, it is about the most useful thing to do on a graph. Now, what if I wanted to find the shortest path on an unweighted graph? How would I do that? Don't give me a ring, give me an algorithm. If I give you an unweighted graph, what would be the way that you would find the shortest path from A to B? BFS. Does everybody agree that what breadth first search did was we started from a vertex? I guess I'm gonna, hold on, sorry. I started from a vertex. I explored all the vertices that were a distance 1 from me. I then did this in oldest order. So anything that was a neighbor of this vertex was a distance of 2, distance of 2, distance of 2, distance of 2. Now anything discovered from here, it'll be a distance of 3. It couldn't have been a distance of less than 3, because if it was a distance of 1, it would have been discovered here. And if it was a distance 2, it would have been discovered when exploring one of these vertices. Okay? So if I give you an unweighted graph, BFS is this way to find the shortest path. And you can do it in linear time in the graph. Any questions? Now what BFS does is find the path with the smallest number of hops. That's sometimes useful. If you wanted, let's say that you were driving a car and you had a very creaky steering wheel, you might not want to make turns. If I ask you what's the fastest way, the best way to drive from here to that store in Bolivia, using the smallest number of turns, that would be a breadth first search graph, wouldn't it? Because basically every time I want to make a turn, I would have to get off the road. That would be kind of a thing. So finding the smallest number of hops is BFS. Unfortunately, in a weighted graph, okay, the one with the smallest number of turns is not always the shortest path. Any of you guys who've ever taken a shortcut, you might imagine a world where, you know, there is, instead of taking a 2-hop path between these two vertices, maybe something where you go through somebody's backyard and then you turn at the swimming pool or something like that is shorter, okay? So the weight of a path in a weighted graph is the sum of the edge weights on that path. The one with the fewest number of edges, a path with the fewest number of edges is not going to be the shortest path, necessarily the shortest weighted path. Any questions? One other caveat here is you probably don't want an algorithm in general that will report all the shortest paths between two nodes. Does everybody see that even a very innocent looking graph can have a huge number of shortest paths between them? Suppose the graph was unweighted. Okay, let's just do this. Suppose this graph was unweighted. How many different paths are there from S to T? Does anybody have an idea?
2 to the power of 4 or
2
something
to the
like that.
power of 4, which is 16. Why is that? At any place I can go up or down. When I get here, up or down, up or down, up or down. I have 4 binary decisions, right? 2 to the 4th different paths. In general, if you say, give me all the shortest paths, you might be waiting, forever to see them printed out on the screen, right? So we want an algorithm that finds a shortest path, not all the shortest paths. Any questions about that? Is that convincing? Sometimes you want all shortest paths. If so, then you need to do something that might be exponential. We'll talk about that when we talk about backtracking, which I think is the next thing we're going to do, okay, after we finish graphs. Any questions? Okay, good. While we're talking about caveats about graphs and shortest paths, okay, one thing to note is that negative edge weights do bad things when it talks about about the shortest path. Let's say I have a graph from S. I'm going to go to this. Let's say the weight of this was 5, 5, 5, 3, minus 100. What is the shortest path from S to T? What's the weight of the shortest path from S to T? Okay. Does anybody have an idea?
We go from S, right, 5, 5, 3, negative 100, and keep going around that triangle as many times.
Does everybody see that if you take the really shortest path from S to T, you never get to T? What is the shortest path from S to T? Keep getting my path is getting more and more and more and more and more negative, right? So negative cost edges, actually specifically negative cost cycles, kind of cause problems in things about shortest paths. Now, usually, if we think of things as distances, like Euclidean distances can never be negative. So we are going to now ignore the possibility of negative cost edges, because it should be clear that negative cost cycles cause big trouble. And the only reason you can have negative cost cycles is if you have negative cost edges. Any questions? Okay. So I am going to now talk about an algorithm. Now, notice, though, that negative cost edges don't cause any problem with minimum spanning tree algorithms. Okay. If we did Kruskal's algorithm, is there ever going to be a cycle? Okay. You're saying, can you just exclude cycles from the path? I don't know quite what that means. Okay. There are algorithms for dealing with graphs that have negative weights but not negative cycles. There's something called the Bellman-Ford algorithm. But in general, I think if we think about this in terms of normal graphs that we see every day, it's rare that we have negative weight edges. Dijkstra's algorithm works only on graphs where there are no negative weight edges, and that's going to be our assumption from now. Any questions? Okay, so what is Dijkstra's algorithm? I was talking with a student today who was very impressed that Dijkstra came up with the original shortest path algorithm in 20 minutes, and he managed to eat off of that for the rest of his life. That's good work if you can get it. Again, the part of the he was thinking about these problems very, very early in the history of algorithms. What is the idea of Dijkstra's algorithm? If I have a shortest path, if the shortest path from S to T goes through X, what do I know? If this is really the shortest path, okay, from S to T, then darn it, you had better use the shortest path from S to X as a prefix. Suppose there was a shorter path from S to X. Does everybody see that using the shorter prefix would reduce the total length of the path from S to T? Okay? So we know as a fact that if we have any shortest path from S to T, we know that every vertex we encounter on that path, okay, we have to know that this is the shortest path for every vertex on the path from S to T. That this is in fact, the prefix is in fact the shortest path from S to that vertex. Okay? Any questions about that reasoning? Okay? If you understand that reasoning, that suggests that the algorithm that we can use to find the shortest path is going to be something that is going to start from S and discover the shortest path to some node. Then discover the shortest path to some other node and keep finding the shortest path to one new node at a time until we find the destination that we care about. Okay, that is the idea of Dijkstra's algorithm. Basically, what do we know? We know that the shortest path from a vertex to itself is going to have a cost of 0, right? If all edge weights are positive, if I have a start from S, if all edge weights are positive, what do I know? What vertex do I know the shortest path from S to? I know the shortest path from S to itself. That's great. Now, is there any way I can enlarge that knowledge? Is there any other vertex that I can claim I know the shortest path from S to it?
The 3 vertices incident to S.
You're saying the 3 vertices incident to it? I don't necessarily know the shortest path from each of the, again, I'm assuming there's a bigger graph out here that I haven't looked at yet.
Oh, okay.
Do I know the shortest path from S to all 3 of these vertices? Is the direct edge the shortest path to is the shortest path from S to here, let's call it Y. Is that the shortest path from S to Y? That direct edge?
No. Well, we don't know.
You don't know is exactly right. What if there was an edge, let's call it here, let's call it Z, and there was something back here that was very cheap? If the cost of getting from S to Z plus the cost of getting from Z to Y was less than the edge S to Y, then I found the shorter path, right? What I want to do with Dijkstra's algorithm, though, is I want to build up a vertex to which I absolutely know the shortest path to it. Suppose the weights of these edges were 7, 8, and let's call it 9. To what vertex do I absolutely know the shortest path from S to it?
To itself, S to S.
S to S, right, that was 0, fine. Now, is there another vertex, just knowing this much of the graph, that I know the shortest path from S to it?
Vertex on the edge with 7, I think it would be.
See this? Oh, why? Because you don't think that's connected to anything? Well, you didn't see. It really is connected to a lot of things.
Never mind.
This is connected to a lot of things. This is connected to a lot of things. What vertex do I know the absolute cheapest way to it?
There's none.
None? Well,
Wait,
I
is that
claim
S
I
or
know that
C
the
or-
cheapest way to get from S to Z here is going to be 3. Why do I know there can't be any cheaper way to get from S to Z? You may say, well, I know that if I start out going to Y, I've already paid a cost of 9. How can I have a cheaper trip to Z if I start out with a cost of 9 than this edge of 3? I could do it if perhaps there was a edge weight of minus 1,000 or something in my graph. But if all the edges are positive, does everybody see that the minimum, the vertex, the neighbor of mine, that is the minimum distance away, I have to know the shortest path to it. Okay? And in general, what I'm going to keep doing is I'm going to build a tree of shortest paths, starting from my start point, of vertices that I know the shortest path from S to that, and grow this one iteration at a time. Do I have an example here? Yes, I do. Suppose I start from this particular vertex here, A. Okay? What vertex do I know the shortest path from A to it? Okay? The one that's 5 away. Does everybody kind of see that? This vertex costs 5. This vertex costs less than or equal to 7. This one costs less than or equal to 12. Right? When I just started looking at the neighbors of A. Now, what is the cheapest vertex I can get to? Well, I now have the choice of going from A. I've got this vertex 5. This edge here tells me there's a way of getting there at cost less than or equal to 12. This thing tells me there's a way of getting to this vertex at a cost of less than or equal to 14, 5 plus 9. But I already know a way of getting to that at a cost of less than or equal to 7. Does everybody agree? Now I've updated it. What is the cheapest way to get from A to another vertex? What's going to be the cheapest way? Okay, I claim I've checked all possibilities. There can't possibly be a better way to get to that vertex than 7. Does everybody agree? Once I've gotten to that, what does that tell me? Well, I look outside the neighbors and say, look, now that I can get here in 7, 7 plus 4 is 11. That's better than 12, right? Now I can get here in a cost of less than 11. Here I can get to it in a cost of less than or equal to 10. Here I can get to it in a cost of less than or equal to 11. That's an improvement, isn't it? Okay. Now, what is the next vertex that I can grab that I will know the cheapest path to it? Does everybody see this? Which vertex should I grab? Does everybody see it's one of the 11s? Why don't I grab this one just for consistency? Oh, actually, no, not the 11. I had a way of getting there at 10. Let's grab that one. Kabunk. Once I graph this, there's a way of getting here in 10. That means I can get from here to here in less than or equal to 12. I can get from here to here in a cost of less than or equal to 17, but I know how to do it in 11, so that's better. What's the next thing I should add? Well, I might as well add this thing. This gives me a way I can get to this vertex at the cost of 11. From here, I can get to this vertex. Actually, from here, I can get to it in a cost of 10 plus 2, which is 12, but I already know how to get to it in 11. I'll grab that. This gives me a way to get to this in a cost of 16. I might as well take the way that costs 12. Does everybody see what I'm doing? Which algorithm does this smell like? Prim's algorithm. Does everybody see that? Prim's algorithm also involved starting from a vertex and one by one adding another vertex to the collection. Does everybody agree? And what is the difference between this and Prim's algorithm? Okay. The amazing thing about is that there's only 4 lines that change between my Prim's algorithm and Dijkstra's algorithm. The first one is I changed the name of my routine from Prim to Dijkstra. Okay? The bigger thing is over here. What did Prim's algorithm do to find a minimum spanning tree? At each iteration, it was looking for the edge that I could grab that would lower, or the vertex to add to the tree by the lowest weight edge. Now I want to grab the vertex that will have the lowest weight, okay, in terms of distance to get to it. A newly discovered edge is interesting. If I have a new edge, what you would call it, PW, okay, or V, let's say I have an edge that goes from V to W. Uh-oh, trouble. I don't know what that's doing. Under what condition is this interesting? If the distance from S to V plus the weight of this edge is less than the best way I already know of getting from W to V, from S to W. If the best way I know of to get to W costs 10, but the distance to get to V is 7, and the weight of an edge from V to W is 2, I have discovered a cheaper way of getting there. And this is the only difference, okay, is that the cheapest way, if the distance to V is greater than the distance to W is greater than the distance to V plus the weight of the new edge, then I've discovered a new way of getting there. And that I've got to update. How did this code look for prims? Does anybody remember? If I wanted to change it back to Prim's algorithm, what do I got to do? I would have to write the word prim here. That much I think you could do. What is the difference between this inner loop for prims and for Dijkstra's algorithm? This is the part of the code where I'm trying to figure out what's the consequence of a newly discovered edge. Okay, can anybody tell me what the changes I have to make to that algorithm is to get it back to prims? Okay, I claim that the cheapest way to get to W in a minimum spanning tree is the weight of the edge. I don't care about how long it took to get to the other endpoint of that edge. So this is the difference to go back to prims. Okay, actually I look at this changed thing and I'm now a little bit I don't even know if that last line changes, quite frankly. Okay? Take a look at this, okay? This is important. I'll briefly discuss it next class. But I want you to take a look at, we're at the end of class, I want you to take a look at Prim's algorithm. Make sure you understand Prim's. Make sure you understand why these changes, okay, enable us to find shortest paths instead of spanning trees. And if you understand that, you'll understand basically the keys to weighted graph algorithms. Any questions? Any questions?